Question 1. Operational review demonstrates that a new utility-scale solar photovoltaic (PV) farm is being planned in a region with significant cloud cover variability. The project team requires accurate data to model the expected energy output and secure financing. Which solar radiation measurement instrument is most appropriate for this scenario to capture the total solar energy available to the PV panels? Option A. Pyranometer. Option B. Pit heliometer. Option C. Anemometer. Option D. Sunshine recorder. Correct answer is A. Pyranometer. Explanation. This scenario presents a professional challenge for an energy manager by requiring them to select the most appropriate solar radiation measurement instrument for a specific, albeit hypothetical, renewable energy project. The challenge lies in understanding the distinct measurement capabilities of different instruments and aligning those capabilities with the project's needs and the relevant regulatory context, which for the Certified Energy Manager (CEM) exam is assumed to be U.S. federal and state energy regulations and best practices. Accurate solar resource assessment is foundational for reliable energy production estimates, system design, and financial modeling, all of which are subject to regulatory scrutiny and industry standards. The correct approach involves selecting the pyranometer for measuring global horizontal irradiance (GI). This is the most appropriate choice because pyranometers are designed to measure the total solar radiation received on a horizontal surface, encompassing both direct and diffuse radiation. This comprehensive measurement is critical for accurately assessing the overall solar energy potential available to a typical photovoltaic (PV) or solar thermal system, which are often designed to capture radiation from all angles. Regulatory bodies and industry standards, such as those promoted by the National Renewable Energy Laboratory (NREL) and referenced in various state energy programs and federal incentives, e.g., investment tax credit guidelines, emphasize the use of GHI data derived from instruments like pyranometers for performance modeling and validation. This aligns with the ethical obligation of an energy manager to ensure the accuracy and reliability of data used for energy project assessments. An incorrect approach would be to select the pit heliometer. While pit heliometers are essential for measuring direct normal irradiance (DNI), which is crucial for concentrating solar power (CSP) technologies, they do not capture diffuse radiation. For a general solar energy project, especially one involving standard PV panels, relying solely on DNI would lead to an underestimation of the total available solar resource, and consequently, the potential energy yield. This would be a failure to adhere to industry best practices for PV system assessment and could lead to misrepresentation of project viability, potentially violating ethical standards and regulatory requirements for accurate reporting. Another incorrect approach would be to select the sunshine recorder. Sunshine recorders, such as the Campbell-Stokes recorder, primarily provide a qualitative or semi-quantitative measure of sunshine duration, hours of bright sunshine, rather than a precise measurement of solar irradiance in watts per square meter. While useful for historical climate analysis or as a supplementary indicator, they lack the quantitative precision required for detailed energy production modeling and system design, which are subject to rigorous regulatory review and financial due diligence. Using such an instrument for primary solar resource assessment would be a significant departure from established industry standards and regulatory expectations for energy project development. Professional decision-making process in such situations should involve a systematic evaluation of project requirements against the capabilities of available measurement technologies. First, clearly define the project's energy technology, e.g., PV, CSP, solar thermal, and its specific energy capture mechanism. Second, identify the relevant solar resource parameters needed for accurate assessment, e.g., GI, DNI, diffuse irradiance. Third, research and understand the measurement principles and output of various solar radiation instruments. Fourth, consult relevant industry standards, regulatory guidelines, and best practices for solar resource assessment in the applicable jurisdiction. Finally, select the instrument that provides the most accurate and appropriate data for the project's specific needs, ensuring compliance with all applicable regulations and ethical obligations. Question 2. Quality control measures reveal that a recently installed solar photovoltaic system's actual energy output is consistently lower than predicted during periods of high solar irradiance. The energy manager is tasked with diagnosing the cause. Which analytical approach best addresses this discrepancy, considering the need for a comprehensive understanding of system performance and resource utilization? Option A. Examine only the raw energy output data to identify trends without considering external factors or efficiency metrics. Option B. Analyze the clearness index to understand atmospheric conditions, the capacity factor to assess how often the system operates at its rated power, and the performance ratio to evaluate the system's efficiency relative to available solar resource. Option C. Prioritize the capacity factor to understand the system's operational uptime and compare it to the theoretical maximum output. Option D. Focus solely on the clearness index to determine if atmospheric conditions are the primary reason for the reduced output. The correct answer is B. Analyze the clearness index to understand atmospheric conditions, the capacity factor to assess how often the system operates at its rated power, and the performance ratio to evaluate the system's efficiency relative to available solar resource. Explanation. This scenario is professionally challenging because it requires the energy manager to interpret complex solar performance data and make informed decisions that impact project viability and regulatory compliance. The challenge lies in moving beyond simple data collection to a nuanced understanding of performance metrics like the clearness index, capacity factor, and performance ratio, and how they relate to expected outcomes and regulatory standards. Careful judgment is required to distinguish between normal operational variations and systemic issues that might necessitate corrective action or impact reporting. The correct approach involves a thorough analysis of the clearness index, capacity factor, and performance ratio in the context of the specific site's meteorological data and the solar installation's design specifications. This approach is right because it directly addresses the core of solar resource assessment and system performance evaluation, which are critical for accurate energy production forecasting, financial modeling, and demonstrating compliance with energy efficiency standards or renewable energy targets. For instance, a consistently low performance ratio, even with a good clearness index, might indicate equipment degradation or operational inefficiencies that need investigation, aligning with the CEM's responsibility to ensure optimal system performance and resource utilization, as often implied in energy management standards and best practices. An incorrect approach that focuses solely on the clearness index without considering the capacity factor or performance ratio fails to capture the actual operational efficiency of the solar system. The clearness index is a measure of atmospheric transparency, not system output. Ignoring the capacity factor, which relates actual output to theoretical maximum output, and the performance ratio, which compares actual output to theoretically possible output given solar resource, leads to an incomplete and potentially misleading assessment. This can result in overestimating or underestimating the system's contribution, potentially violating reporting requirements for energy production or efficiency gains. Another incorrect approach that prioritizes the capacity factor without a deep dive into the performance ratio and clearness index is also flawed. While the capacity factor indicates how often the plant is operating at its rated power, it doesn't explain why it's not achieving its theoretical maximum. Without considering the clearness index and performance ratio, the energy manager cannot diagnose whether low capacity factor is due to insufficient solar resource, low clearness index, or system inefficiencies, low performance ratio. This lack of diagnostic capability hinders effective problem solving and can lead to missed opportunities for performance improvement, potentially contravening the CEM's duty to maximize energy system efficiency. A third incorrect approach that solely examines raw energy output data without analyzing the clearness index, capacity factor, or performance ratio is fundamentally inadequate. Raw output alone provides no context for evaluating the system's efficiency or its response to varying solar conditions. It's like measuring a car's speed without considering the road conditions or the engine's fuel efficiency. This approach fails to provide the analytical depth required for effective energy management and could lead to incorrect conclusions about the system's performance, potentially resulting in non-compliance with reporting standards that require performance metrics. The professional decision-making process for similar situations should involve a systematic evaluation of all relevant performance indicators. This includes understanding the theoretical underpinnings of each metric, clearness index, capacity factor, performance ratio, their interdependencies, and how they relate to the specific installation's design and operational context. The energy manager should then compare observed data against expected values derived from reliable meteorological data and system specifications. Any significant deviations should trigger a diagnostic investigation, prioritizing approaches that offer the most comprehensive understanding of system performance and potential issues, thereby ensuring accurate reporting and optimal resource utilization. Question 3. Stakeholder feedback indicates a strong desire to implement solar thermal technology for water heating within a large commercial facility. However, concerns have been raised regarding the long-term cost-effectiveness and potential regulatory hurdles. As the certified energy manager, what is the most appropriate approach to address these concerns and move forward with a viable project, adhering strictly to U.S. regulatory frameworks and professional energy management guidelines? Option A. Proceed with the installation of the chosen solar thermal system immediately to capitalize on current market conditions, addressing any regulatory compliance issues that may arise during or after the installation. Option B. Select a novel, cutting-edge solar thermal technology that has been highly praised in industry publications, assuming it will offer superior performance and quickly gain regulatory approval. Option C. Prioritize the selection of the solar thermal system with the lowest initial purchase price, as this will directly address stakeholder concerns about upfront investment and demonstrate immediate cost savings. Option D. Conduct a comprehensive feasibility study that includes a detailed technical assessment of suitable solar thermal technologies, an analysis of life cycle costs, and a thorough review of all applicable U.S. federal, state, and local regulation, including building codes and permitting requirements. The correct answer is D. Conduct a comprehensive feasibility study that includes a detailed technical assessment of suitable solar thermal technologies, an analysis of life cycle costs, and a thorough review of all applicable U.S. federal, state, and local regulations, including building codes and permitting requirements. Explanation: this scenario presents a professional challenge because it requires balancing stakeholder expectations with the practical and regulatory realities of implementing solar thermal technology. The challenge lies in managing diverse interests, including cost-effectiveness, environmental impact, and regulatory compliance, while ensuring the chosen technology aligns with the organization's energy management goals and applicable standards. Careful judgment is required to navigate these competing demands and select a solution that is both technically sound and ethically responsible. The correct approach involves a thorough technical and economic feasibility study that considers the specific site conditions, available solar resources, and the organization's energy needs, all within the framework of relevant U.S. federal and state regulations governing renewable energy installations and building codes. This approach prioritizes data-driven decision-making and adherence to established standards, ensuring that the proposed solar thermal system is not only efficient, but also compliant with all legal and safety requirements. This aligns with the professional responsibilities of an energy manager to implement sustainable solutions that are technically viable and legally sound, as mandated by professional codes of conduct and regulatory frameworks like those overseen by the Department of Energy and state-level energy offices. An incorrect approach that focuses solely on the lowest upfront cost without a comprehensive feasibility study fails to account for long-term operational costs, maintenance, and potential performance issues, potentially violating principles of responsible resource management and fiduciary duty. This could lead to a system that underperforms or requires costly retrofits, ultimately failing to meet energy reduction targets. Another incorrect approach that prioritizes a specific, unproven solar thermal technology based on anecdotal evidence or marketing claims, without rigorous technical validation and regulatory review, risks non-compliance with building codes, safety standards, and environmental regulations. This bypasses essential due diligence and could result in a system that is unsafe, inefficient, or ineligible for incentives, leading to financial and reputational damage. A third incorrect approach that ignores local zoning ordinances and permitting requirements in favor of rapid deployment overlooks critical legal obligations. Failure to secure necessary permits can lead to fines, project delays, or even mandatory system removal, demonstrating a disregard for the rule of law and professional integrity. Professionals should employ a decision-making framework that begins with a clear understanding of project objectives and constraints. This involves conducting thorough site assessments, evaluating multiple technology options based on objective performance data and life cycle cost analysis, and rigorously reviewing all applicable federal, state, and local regulations. Engaging with relevant stakeholders, including technical experts, legal counsel, and regulatory bodies, throughout the process is crucial for ensuring compliance and successful implementation. The ultimate decision should be based on a holistic evaluation that balances technical merit, economic viability, environmental impact, and strict adherence to all legal and ethical requirements. Question 4. Stakeholder feedback indicates concerns regarding the perceived responsiveness and operational stability of a wind farm's control systems, alongside anecdotal reports of unusual vibrations emanating from the nacelle during high wind events. As the certified energy manager responsible for this U.S.-based facility, what is the most ethically and regulatorily sound initial course of action? Option A. Schedule a meeting with the stakeholders to explain that wind turbine operations are complex and that minor vibrations are often within normal operating parameters, deferring any technical investigation until a more convenient time. Option B. Focus solely on the reported control system responsiveness, as this is a direct operational parameter, and postpone any investigation into nacelle vibrations until more concrete evidence of a problem emerges. Option C. Initiate a comprehensive diagnostic review of the turbine control systems and conduct a detailed structural and mechanical inspection of the nacelles, prioritizing any findings that could impact safety or regulatory compliance, and consult relevant EPA and OSHA guidelines for operational standards. Option D. Immediately adjust the control system parameters to reduce turbine speed during high wind events, as this is a common practice to mitigate stress on components and inform stakeholders that their concerns are being addressed. The correct answer is C. Initiate a comprehensive diagnostic review of the turbine control systems and conduct a detailed structural and mechanical inspection of the nacelles, prioritizing any findings that could impact safety or regulatory compliance, and consult relevant EPA and OSHA guidelines for operational standards. Explanation. This scenario presents a professional challenge due to conflicting priorities and potential impacts on operational efficiency and safety. As a certified energy manager, CEM, the professional is tasked with balancing stakeholder concerns, regulatory compliance, and the optimal performance of renewable energy assets. The ethical dilemma arises from the need to address feedback that may not align with immediate technical recommendations or established maintenance protocols, while also ensuring the long-term viability and safety of the wind turbine infrastructure. Careful judgment is required to navigate these competing interests without compromising professional integrity or the integrity of the energy generation process. The correct approach involves a thorough, data-driven investigation into the stakeholder feedback, prioritizing safety and regulatory adherence. This means meticulously examining the reported issues related to blade performance, nacelle integrity, generator efficiency, and control system responsiveness. The CEM must consult relevant U.S. regulatory frameworks, such as those established by the Environmental Protection Agency, EPA, concerning emissions and environmental impact, and potentially Occupational Safety and Health Administration, OSHA, guidelines for workplace safety during inspections and maintenance. The ethical justification for this approach lies in the CEM's professional responsibility to ensure the safe, efficient, and compliant operation of energy systems. This proactive and investigative stance upholds the principles of due diligence and responsible energy management, aligning with the ethical codes expected of CEM professionals. An incorrect approach would be to dismiss the stakeholder feedback outright without proper investigation. This failure stems from a disregard for potential operational deficiencies or safety concerns that could be signaled by the feedback. Ethically, this demonstrates a lack of due diligence and a potential violation of the CEM's duty to act in the best interest of the project and its stakeholders. From a regulatory standpoint, ignoring potential issues could lead to noncompliance with environmental or safety regulations, resulting in penalties and reputational damage. Another incorrect approach would be to implement immediate, unverified modifications to the turbine components based solely on the feedback, without a comprehensive technical assessment or consideration of regulatory implications. This hasty action risks introducing new problems, compromising the turbine's performance, or even violating specific operational parameters set by manufacturers or regulatory bodies. The ethical failure here is acting without sufficient expertise and data, potentially leading to unintended negative consequences. A third incorrect approach involves prioritizing cost-cutting measures over addressing the reported issues, even if the feedback suggests potential performance degradation or safety risks. This approach prioritizes short-term financial gains over long-term operational integrity and safety, which is ethically unsound and can lead to significant regulatory violations if the issues impact environmental compliance or worker safety. The professional decision-making process for similar situations should involve a structured approach. 1. Acknowledge and document all stakeholder feedback. 2. Conduct a preliminary risk assessment to prioritize concerns based on potential safety, environmental, and operational impacts. 3. Initiate a thorough technical investigation, consulting relevant manufacturer specifications and U.S. regulatory guidelines. 4. Develop a data-driven plan for addressing validated issues, considering the most efficient and compliant solutions. 5. Communicate findings and proposed actions transparently to stakeholders. 6. Implement approved solutions with proper oversight and verification. Question 5. Upon reviewing a potential solar thermal system installation for a commercial building in a region with moderate solar irradiance and significant diurnal temperature variations, which approach best ensures the selection of the most appropriate collector technology, considering both performance and long-term operational efficiency? Option A. Selecting evacuated tube collectors due to their superior performance in low-temperature conditions and reduced heat loss, which are beneficial in a climate with significant diurnal temperature swings. Option B. Prioritizing flat-plate collectors solely based on their generally lower initial purchase price compared to other solar thermal technologies. Option C. Choosing the collector type that has been most widely adopted in similar commercial installations without specific regard for the local climate or building's energy demand profile. Option D. Opting for concentrating collectors, assuming their higher efficiency at peak solar intensity will offset any potential challenges in diffuse light conditions. Correct answer is A. Selecting evacuated tube collectors due to their superior performance in low-temperature conditions and reduced heat loss, which are beneficial in a climate with significant diurnal temperature swings. Explanation. This scenario presents a professional challenge because selecting the most appropriate solar thermal collector technology requires a nuanced understanding of site-specific conditions, performance characteristics, and regulatory compliance, rather than a one-size-fits-all approach. A certified energy manager, CEM, must balance technical efficacy with economic viability and adherence to relevant standards. The correct approach involves a comprehensive impact assessment that considers the specific climate, available space, and intended application of the solar thermal system, aligning with the principles of responsible energy management and the guidelines for efficient system design and implementation. This approach is justified by the need to maximize energy yield, ensure long-term system performance, and meet any applicable local or national energy efficiency standards or building codes that may implicitly favor certain technologies based on their demonstrated performance in specific environmental conditions. For instance, regulations might encourage technologies proven to be effective in low-insulation environments or those that minimize thermal losses in colder climates. An incorrect approach would be to solely prioritize the lowest upfront cost without a thorough evaluation of long-term operational efficiency and maintenance requirements. This fails to meet the professional obligation of ensuring a cost-effective and sustainable energy solution, potentially leading to underperformance and higher lifecycle costs, which could violate principles of prudent financial management and energy stewardship. Another incorrect approach would be to select a collector type based on its perceived technological sophistication, without verifying its suitability for the specific application and climate. This overlooks the critical need for a practical and effective solution, potentially leading to system failure or suboptimal performance, and could be seen as a failure to exercise due diligence in system selection. A further incorrect approach would be to ignore potential environmental impacts or site-specific constraints, such as shading or structural limitations, when choosing a collector technology. This demonstrates a lack of holistic assessment and could lead to non-compliance with environmental regulations or building codes, compromising the project's overall feasibility and sustainability. Professionals should employ a decision-making framework that begins with a thorough site assessment and needs analysis, followed by a comparative evaluation of different solar thermal collector technologies based on their performance data, life cycle costs, maintenance needs, and suitability for the local climate and intended application. This evaluation should be informed by relevant industry, best practices, and any applicable regulatory requirements for energy systems. Question 6. Governance review demonstrates that a proposed solar PV installation project is targeting a specific level of energy output. To maximize this output, the project team is considering PV modules with the highest reported efficiency ratings. However, the project manager has raised concerns about the novel encapsulation materials and advanced, less tested substrate technologies used in these high-efficiency modules, suggesting a potential risk to long-term durability and performance compared to modules with more conventional construction. As the certified energy manager, what approach best balances the pursuit of high efficiency with the imperative of reliable and safe energy generation, adhering to established industry practices and regulatory expectations for PV installations? Option A. Rely exclusively on the manufacturer's claims of efficiency and durability without conducting independent verification or assessing the specific materials and encapsulation techniques employed in the module's construction. Option B. Select PV modules based solely on the highest reported efficiency ratings, assuming that advanced technologies inherently translate to superior long-term performance and reliability. Option C. Opt for PV modules that offer the lowest upfront cost, even if they employ less common materials or simplified encapsulation, as long as they meet the minimum stated efficiency requirements. Option D. Prioritize PV modules that utilize well-established, certified materials and encapsulation methods with a proven track record of durability and performance under expected environmental conditions, ensuring compliance with relevant industry standards for safety and reliability. The correct answer is D. Prioritize PV modules that utilize well-established, certified materials and encapsulation methods with a proven track record of durability and performance under expected environmental conditions, ensuring compliance with relevant industry standards for safety and reliability. Explanation: this scenario is professionally challenging because it requires an energy manager to balance the pursuit of higher module efficiency with the potential risks associated with novel or less proven materials and encapsulation techniques. The challenge lies in ensuring that the chosen PV module construction, while aiming for improved performance, does not compromise long-term reliability, safety, or compliance with relevant standards, which could lead to premature failure, increased maintenance costs, or even safety hazards. Careful judgment is required to assess the trade-offs between efficiency gains and potential risks. The correct approach involves prioritizing PV modules that utilize well-established, certified materials and encapsulation methods that have a proven track record of durability and performance under the expected environmental conditions. This approach aligns with the fundamental principles of responsible energy management, which emphasize reliability, safety, and adherence to industry standards. Specifically, it would involve selecting modules that meet or exceed relevant certifications, e.g., IEC standards for PV modules, and have undergone rigorous testing for degradation, weather resistance, and electrical safety. This ensures that the investment in renewable energy infrastructure is sound and sustainable, minimizing the risk of costly failures and ensuring the intended energy output over the module's lifespan. An incorrect approach that focuses solely on the highest reported module efficiency without considering the underlying construction materials and encapsulation methods is professionally unacceptable. This failure stems from a disregard for the established safety and performance standards that govern PV module manufacturing. For instance, using unproven encapsulation materials that may degrade rapidly under UV exposure or humidity could lead to delamination and moisture ingress, causing electrical faults and premature module failure, thereby violating the implicit warranty of performance and potentially safety regulations. Another incorrect approach that prioritizes cost reduction by selecting modules with substandard materials or simplified encapsulation processes, even if they meet basic efficiency claims, is also professionally unsound. This approach neglects the long-term economic and environmental implications of reduced module lifespan and increased failure rates. It may also contravene ethical obligations to ensure the responsible use of resources and the delivery of reliable energy solutions. Such a choice could lead to higher life cycle costs due to frequent replacements and repairs, undermining the economic viability of the renewable energy project and potentially violating contractual obligations for performance. A third incorrect approach that relies on manufacturer-provided efficiency data without independent verification or consideration of the materials and encapsulation used is also problematic. While manufacturer data is a starting point, it does not replace the need for due diligence. Relying solely on such data without understanding the construction can lead to selecting modules that may achieve high efficiency under ideal laboratory conditions, but perform poorly in real-world applications due to material limitations or encapsulation vulnerabilities. This can result in a failure to meet project performance targets and a breach of the duty of care expected of an energy manager. The professional decision-making process for similar situations should involve a comprehensive risk assessment that considers not only efficiency, but also the materials, encapsulation, manufacturing quality, and relevant certifications of PV modules. This includes 1. Understanding the project's specific environmental conditions and performance expectations. 2. Researching and verifying module certifications and compliance with relevant industry standards. 3. Evaluating the track record and reliability of the chosen materials and encapsulation techniques. 4. Considering the manufacturer's warranty and reputation. 5. Performing a life cycle cost analysis that accounts for potential degradation and failure rates. Question 7. The evaluation methodology shows a proposed wind resource assessment for a new wind farm development. The project team is considering several approaches to determine the wind speed, wind direction, and wind shear at the proposed site. Which of the following approaches best aligns with the rigorous standards expected for a certified energy manager, CEM, in conducting such an assessment? Option A. Employing data from a single, uncalibrated anemometer located on a temporary structure, without cross-referencing with any historical or regional wind data. Option B. Utilizing a combination of on-site meteorological mast measurements at multiple heights, calibrated instruments, and validated long-term wind data from a nearby reference station, all analyzed in accordance with recognized industry standards for wind resource assessment. Option C. Using wind speed data from a single anemometer at a representative height, without specific consideration for how wind speed changes with altitude, wind shear. Option D. Relying exclusively on publicly available wind resource maps and general regional wind data, as these provide a broad overview of potential wind resources. The correct answer is B. Utilizing a combination of on-site meteorological mast measurements at multiple heights, calibrated instruments, and validated long-term wind data from a nearby reference station, all analyzed in accordance with recognized industry standards for wind resource assessment. Explanation. The evaluation methodology shows a scenario where a certified energy manager, CEM, is tasked with assessing wind resources for a potential renewable energy project. This scenario is professionally challenging because the accuracy and reliability of the wind resource assessment directly impact the project's feasibility, financial projections, and ultimately, its success. Misinterpreting or inadequately assessing wind speed, direction, and shear can lead to significant underestimation or overestimation of energy production, resulting in poor investment decisions, non-compliance with performance guarantees, and potential environmental impact miscalculations. CEM must apply a rigorous and ethically sound methodology that aligns with established industry, best practices, and regulatory expectations for such assessments. The correct approach involves utilizing a combination of on-site measurements from meteorological masts, MET masts, equipped with calibrated anemometers and wind vanes, supplemented by validated long-term wind data from nearby reference stations or reputable meteorological models. This approach ensures that the assessment captures site-specific wind characteristics, including diurnal and seasonal variations, turbulence intensity, and importantly, wind shear. Wind shear, the change in wind speed with height, is critical for optimizing turbine selection and placement, and its accurate determination requires measurements at multiple heights. Adherence to recognized standards, such as those outlined by the International Electrotechnical Commission, (IC), or relevant national energy agencies, is paramount. This ensures data quality, transparency, and defensibility of the assessment, aligning with the ethical obligation to provide accurate and reliable information to stakeholders and regulatory bodies. An incorrect approach would be to rely solely on publicly available wind maps or generic regional data without on-site validation. This fails to account for local topographical influences, obstructions, and microclimatic variations that significantly affect wind speed and direction. Such an approach is ethically flawed as it presents an incomplete and potentially misleading picture of the resource, violating the CEM's duty to provide accurate assessments. Another incorrect approach is to use data from a single measurement height without considering wind shear. This overlooks a crucial factor in wind energy project design, leading to suboptimal turbine selection and energy yield predictions, and potentially violating regulatory requirements for comprehensive resource assessment. Furthermore, failing to calibrate or maintain measurement equipment, or not using validated data sources, introduces significant uncertainty and compromises the integrity of the assessment, which is an ethical and professional failing. Professionals should approach wind resource assessment by first understanding the specific regulatory requirements and industry standards applicable to the project's jurisdiction. This involves identifying the accepted methodologies for data collection, analysis, and reporting. A robust decision-making process would involve 1. Defining the project's objectives and required accuracy level. 2. Selecting appropriate measurement technologies and siting strategies based on site characteristics and regulatory guidance. 3. Implementing a comprehensive data quality assurance and quality control (COS/QC) plan. 4. Performing thorough analysis of wind speed, direction, and shear, considering long-term trends and variability. And 5. Transparently documenting all assumptions, methodologies, and results, including any limitations. This systematic and evidence-based approach ensures that the assessment is both technically sound and ethically defensible. Question 8. Examination of the data shows a client is interested in incorporating solar space heating into their existing residential property to reduce energy costs and their carbon footprint. They are open to both active and passive solar heating system concepts. As the certified energy manager, what is the most appropriate approach to advising the client, considering the need for regulatory compliance and practical implementation? Option A. Recommend a passive solar design strategy, emphasizing its inherent simplicity and potential for significant heat gain through architectural modifications, while ensuring the proposed modifications align with local building codes and structural integrity requirements. Option B. Suggest a hybrid approach, recommending a combination of passive design elements and an active solar thermal system, but without conducting a detailed site-specific analysis to determine the optimal configuration or verifying compliance with all applicable energy codes and zoning regulations. Option C. Advise the client that passive solar heating is generally more cost-effective and simpler to implement, and therefore focus solely on this option without thoroughly exploring the potential benefits and regulatory considerations of active systems. Option D. Propose an active solar thermal system, highlighting its direct heat generation capabilities, and proceed with system design and procurement without detailed verification of local permitting requirements or integration with the existing HVAC system. The correct answer is A. Recommend a passive solar design strategy, emphasizing its inherent simplicity and potential for significant heat gain through architectural modifications, while ensuring the proposed modifications align with local building codes and structural integrity requirements. Explanation. This scenario presents a professional challenge for an energy manager tasked with advising a client on solar space heating systems. The challenge lies in balancing the client's desire for cost-effectiveness and environmental benefit with the need to adhere to relevant building codes, energy efficiency standards, and potentially local zoning ordinances that govern the installation of solar technologies. The energy manager must ensure that any proposed system is not only technically sound, but also legally compliant and ethically presented. The correct approach involves a thorough assessment of both active and passive solar heating system options, considering their performance characteristics, installation requirements, and integration with existing building infrastructure. This approach prioritizes understanding the specific climate, building orientation, and client's energy needs to recommend the most suitable and compliant solution. Regulatory justification stems from the energy manager's professional responsibility to ensure that recommendations align with established energy codes, e.g., International Energy Conservation Code (IC), or state-specific amendments, and building safety standards. Ethical considerations demand transparency about the limitations and benefits of each system, ensuring the client makes an informed decision based on accurate, compliant information. An incorrect approach would be to solely focus on the theoretical efficiency of a passive system, without considering the practicalities of its implementation within the existing building envelope, or its compliance with structural and fire safety regulations. This fails to acknowledge the regulatory framework that dictates building modifications. Another incorrect approach is to recommend an active solar heating system based purely on its potential for higher energy generation, without verifying its compatibility with the building's existing heating distribution network or its adherence to electrical codes and permitting requirements. This overlooks critical compliance and safety aspects. Finally, recommending a system without considering the client's specific site conditions and local climate, and without verifying compliance with any applicable renewable energy incentives or permitting processes, demonstrates a failure to provide comprehensive and actionable advice, potentially leading to non-compliance and wasted investment. Professionals should approach such situations by first identifying all applicable regulatory frameworks, including building codes, energy efficiency standards, and local ordinances. This is followed by a detailed site assessment and client needs analysis. Subsequently, a comparative evaluation of technically feasible and compliant solar heating options, both active and passive, should be conducted, focusing on their performance, cost-effectiveness, and integration feasibility. The final recommendation must be supported by clear justification, including projected energy savings, environmental benefits, and crucially, confirmation of compliance with all relevant regulations. Question 9. Assessment of the most effective strategy for a certified energy manager, CEM, to ensure the successful development and grid integration of a new wind farm project, considering turbine sizing, site selection, and regulatory compliance within the United States. Option A. Focus on securing the lowest cost turbine technology and a site with minimal upfront development costs, deferring detailed grid integration studies and regulatory approval processes until after the primary equipment and location are secured. Option B. Prioritize selecting the largest, most energy-efficient turbines available to maximize potential energy generation, and then identify a suitable site that can accommodate them, addressing grid integration and regulatory issues as they arise during the later stages of development. Option C. Conduct a comprehensive feasibility study that includes detailed site assessments, thorough regulatory compliance checks, and early engagement with the relevant grid operator to determine interconnection requirements and capacity before finalizing turbine sizing and technology selection. Option D. Begin the project by performing detailed wind resource assessments and turbine performance simulations to optimize energy output, and then engage with grid operators and regulatory bodies only after the optimal turbine configuration and site have been technically determined. The correct answer is C. Conduct a comprehensive feasibility study that includes detailed site assessments, thorough regulatory compliance checks, and early engagement with the relevant grid operator to determine interconnection requirements and capacity before finalizing turbine sizing and technology selection. Explanation. This scenario presents a common challenge for certified energy managers, CEM, involved in renewable energy projects, specifically wind power. The professional challenge lies in balancing the technical feasibility of turbine design and site selection with the complex regulatory landscape and grid integration requirements. A CEM must navigate these factors to ensure a project is not only technically sound and economically viable, but also compliant with all applicable laws and guidelines, and that it can be reliably connected to the existing electrical infrastructure. This requires a holistic understanding that extends beyond pure engineering to encompass policy, environmental considerations, and grid stability. The correct approach involves a comprehensive assessment that prioritizes regulatory compliance and grid integration feasibility from the outset, alongside technical design and site suitability. This means understanding and adhering to the specific regulations governing renewable energy development, environmental impact assessments, and grid connection standards within the relevant jurisdiction. For a CEM, this translates to proactively engaging with regulatory bodies, grid operators, and stakeholders to ensure all requirements are met. This approach is ethically sound and professionally responsible because it minimizes project risks, prevents costly redesigns or delays due to noncompliance, and ensures the long-term operational success and safety of the wind turbine installation. It aligns with the CEM's duty to promote energy efficiency and sustainability in a manner that is both effective and lawful. An incorrect approach that focuses solely on maximizing energy output through turbine sizing without considering grid capacity or regulatory approvals is professionally flawed. This failure stems from a disregard for the established legal and technical frameworks that govern energy infrastructure. Such an approach risks significant project delays, fines, or outright rejection by grid operators and regulatory authorities. It also poses a potential risk to grid stability if the turbine's output cannot be managed or integrated safely. Another incorrect approach that prioritizes the lowest cost of turbine technology without a thorough site-specific assessment and grid integration study is also professionally unacceptable. While cost is a factor, it cannot supersede regulatory compliance and technical feasibility. This approach neglects the critical need to ensure the chosen turbine is suitable for the specific site conditions, wind resource, terrain, environmental sensitivities, and that it can be reliably connected to the grid without causing disruptions or requiring excessive, unbudgeted grid upgrades. Regulatory frameworks often mandate specific environmental and safety standards that must be met, and grid operators have technical requirements for interconnection that cannot be ignored for cost savings. A third incorrect approach that delays engagement with grid operators until after turbine selection and initial site assessment is also problematic. This oversight can lead to significant challenges if the chosen turbine technology or site location presents unforeseen integration issues, or if the grid operator has capacity limitations or specific technical requirements that were not anticipated. Regulatory frameworks often stipulate a phased approach to grid connection applications, and failing to engage early can result in missed deadlines, increased costs for necessary grid upgrades, or even the inability to connect the turbine to the grid at all, rendering the project infeasible. Professionals should adopt a phased, integrated decision-making process. This begins with a thorough understanding of the regulatory environment and grid operator requirements for the specific jurisdiction. This understanding informs the initial site selection and turbine technology evaluation. Early and continuous engagement with all relevant stakeholders, including regulatory bodies and grid operators, is crucial. This iterative process allows for the identification and mitigation of potential issues early on, ensuring that technical design choices are aligned with regulatory mandates and grid integration capabilities, thereby maximizing the probability of a successful and compliant project. Question 10. Which approach would be most appropriate for a certified energy manager to use when determining the solar radiation resource for a new commercial solar photovoltaic project seeking regulatory approval and potential incentives in the United States, ensuring compliance with relevant energy codes and standards? Option A. Downloading readily available solar insolation data from a general weather website that provides monthly averages for the nearest major city. Option B. Using a simplified online calculator that estimates solar potential based on the project's general geographic region and installed capacity, without detailed site-specific analysis. Option C. Employing a validated solar resource assessment tool that utilizes satellite-derived data, ground-based measurements, and meteorological models calibrated to the specific project location and time period, and aligned with standards recognized by the U.S. Department of Energy or relevant state energy agencies. Option D. Relying solely on historical weather station data from the past 5 years for the closest meteorological station, without considering any specific solar resource assessment methodologies or validation. The correct answer is C. Employing a validated solar resource assessment tool that utilizes satellite-derived data, ground-based measurements, and meteorological models, calibrated to the specific project location and time period, and aligned with standards recognized by the U.S. Department of Energy or relevant state energy agencies. Explanation. This scenario is professionally challenging because a certified energy manager, CEM, must balance the technical aspects of solar resource assessment with the regulatory requirements for accurate and defensible data. The challenge lies in selecting a methodology that not only provides a reasonable estimate of solar radiation, but also aligns with the specific standards and guidelines mandated by the relevant regulatory bodies for energy projects, particularly those seeking incentives or compliance with energy codes. The choice of approach directly impacts the project's feasibility, financial projections, and regulatory approval. The correct approach involves utilizing a methodology that is recognized and accepted by the governing regulatory framework for energy assessments. This typically means employing industry-standard tools and databases that have been validated for accuracy and are commonly used in regulatory submissions. Such an approach ensures that the solar radiation data used for energy production estimates is credible, auditable, and meets the requirements for demonstrating compliance or eligibility for programs. The regulatory justification stems from the need for standardized, reliable data to ensure fair competition, accurate performance verification, and the integrity of energy policy implementation. Ethical considerations also demand transparency and accuracy in reporting to stakeholders and regulatory agencies. An incorrect approach that relies on readily available but unverified online data sources fails to meet regulatory scrutiny. These sources may lack the necessary validation, geographical specificity, or temporal resolution required for a formal energy assessment. Regulatory failure lies in presenting data that cannot be substantiated or defended under established guidelines, potentially leading to project rejection or penalties. Another incorrect approach, using a simplified estimation method without considering site-specific obstructions or atmospheric conditions, also falls short. This method, while perhaps quick, lacks the precision demanded by regulations that often require detailed site analysis to account for real-world performance variations. The ethical failure here is a lack of due diligence and a potential misrepresentation of the project's energy potential. A third incorrect approach, focusing solely on historical weather data without accounting for future climate trends or specific solar resource assessment standards, is also problematic. While historical data is a component, regulations often require a forward-looking perspective or adherence to specific solar resource assessment protocols that go beyond simple historical averages, leading to a regulatory and ethical failure in providing a robust and compliant assessment. Professional decision-making in such situations requires a systematic process. First, identify the specific regulatory framework and guidelines applicable to the project. Second, research and evaluate available solar radiation assessment methodologies against these requirements, prioritizing those that are validated, industry standard, and commonly accepted by regulatory bodies. Third, select the methodology that offers the best balance of accuracy, cost-effectiveness, and regulatory compliance. Finally, document the chosen methodology and its justification thoroughly to ensure transparency and auditability. Question 11. Implementation of a solar resource assessment for a proposed commercial rooftop solar photovoltaic system in the United States requires careful consideration of data sources and analytical methods to ensure compliance with Certified Energy Manager (CEM) standards and relevant U.S. energy regulations. Which of the following approaches best aligns with these requirements? Option A. Focusing exclusively on theoretical sun path diagrams and solar angles, without incorporating actual measured or reliably modeled solar irradiance data or a detailed site-specific shading analysis. Option B. Utilizing publicly available, validated solar irradiance data from the National Renewable Energy Laboratory (NREL), applying standard industry methodologies for sun path and solar angle calculations, and conducting a site-specific shading analysis considering relevant obstructions. Option C. Relying solely on a single, unverified online solar calculator for irradiance data and performing a generic shading analysis without site-specific considerations. Option D. Using historical weather data from a distant, climatically dissimilar location for irradiance assessment, and conducting a generalized shading analysis without accounting for specific site obstructions. The correct answer is B. Utilizing publicly available, validated solar irradiance data from the National Renewable Energy Laboratory (NREL), applying standard industry methodologies for sun path and solar angle calculations, and conducting a site-specific shading analysis considering relevant obstructions. Explanation. This scenario is professionally challenging because it requires balancing the technical requirements of solar resource assessment with the specific regulatory compliance mandated by the Certified Energy Manager (CEM) program, which in this context is assumed to operate under U.S. federal and state energy regulations. A thorough understanding of solar irradiance data, sun path diagrams, solar angles, and shading analysis is crucial for accurate system design and performance prediction. However, the primary challenge lies in ensuring that the chosen methodologies and data sources align with the established standards and guidelines that a CEM professional is expected to adhere to, as these regulations often dictate acceptable practices for energy project development and reporting. The correct approach involves utilizing publicly available, validated solar irradiance data from sources like the National Renewable Energy Laboratory, NREL, and applying standard industry methodologies for sun path and solar angle calculations, while conducting a site-specific shading analysis that considers obstructions relevant to the proposed installation location. This approach is correct because it directly aligns with the principles of due diligence and regulatory compliance expected of a CEM. NREL data is widely recognized and accepted by regulatory bodies for energy project assessments in the U.S. Standard calculation methods ensure consistency and comparability, and a site-specific shading analysis is essential for accurate energy yield predictions, which are often subject to regulatory scrutiny and financial incentives. Adhering to these established, verifiable methods demonstrates professional competence and ensures that the assessment meets the requirements for potential permitting, financing, or incentive applications governed by U.S. energy regulation. An incorrect approach that relies solely on a single, unverified online solar calculator without cross-referencing with established databases or considering site-specific shading factors fails to meet regulatory expectations. This is a regulatory failure because it bypasses the requirement for using reliable, validated data sources that are typically referenced or implicitly required by energy regulations for project feasibility studies. Such an approach lacks the rigor necessary for professional certification and could lead to inaccurate energy production estimates, potentially resulting in noncompliance with performance guarantees or incentive program requirements. Another incorrect approach that uses historical weather data from a distant, climatically dissimilar location for irradiance assessment, while performing a generic shading analysis without considering the specific site's obstruction, is also professionally unacceptable. This represents a significant regulatory and ethical failure. It is a regulatory failure because energy regulations often implicitly or explicitly require data relevant to the project's actual location to ensure accurate performance predictions and to avoid misleading stakeholders. It is an ethical failure as it can lead to misrepresentation of the project's potential, impacting investment decisions, and potentially leading to financial losses for stakeholders. A third incorrect approach that focuses exclusively on theoretical sun path diagrams without incorporating actual measured or reliably modeled solar irradiance data, and a detailed shading analysis for the specific site is also flawed. While understanding sun paths is foundational, it is insufficient on its own for a comprehensive solar resource assessment required by regulatory frameworks. This approach fails to meet regulatory requirements for a practical and accurate assessment of available solar energy, which is critical for determining system size, economic viability, and compliance with energy efficiency standards or renewable energy mandates. A professional decision-making process for similar situations should involve a systematic evaluation of available data and methodologies against the specific requirements of the CEM certification and relevant U.S. energy regulations. This includes identifying authoritative data sources, e.g., NREL, NOAA, understanding accepted industry calculation standards, and prioritizing site-specific analysis for factors like shading. Professionals should always seek to use validated, verifiable information and transparent methodologies to ensure the integrity and compliance of their assessments. When in doubt, consulting regulatory guidance documents or seeking clarification from relevant authorities is a prudent step. Question 12. Risk assessment procedures indicate that a concentrated solar power (CSP) facility is experiencing fluctuations in its capacity factor and efficiency metrics. The facility's environmental impact report highlights potential concerns regarding water usage and thermal emissions. As a certified energy manager operating under U.S. regulatory frameworks, which approach best ensures compliance and responsible operation? Option A. Prioritize achieving the highest possible energy conversion efficiency, even if it means temporarily reducing the plant's overall output and potentially overlooking minor environmental reporting discrepancies. Option B. Address the reported environmental concerns by implementing new mitigation technologies without first investigating the underlying CSP performance data for efficiency and capacity factor to avoid any potential operational disruptions. Option C. Focus exclusively on increasing the plant's capacity factor to meet energy demand targets, assuming that higher output inherently justifies any minor deviations in efficiency or environmental reporting. Option D. Conduct a detailed analysis of the CSP plant's operational data to identify the root causes of efficiency and capacity factor variations, and then assess how these variations directly influence the reported environmental impacts, ensuring all mitigation strategies align with EPA guidelines and permit conditions. Correct answer is D. Conduct a detailed analysis of the CSP plant's operational data to identify the root causes of efficiency and capacity factor variations, and then assess how these variations directly influence the reported environmental impacts, ensuring all mitigation strategies align with EPA guidelines and permit conditions. Explanation: this scenario is professionally challenging because it requires balancing operational efficiency, environmental stewardship, and regulatory compliance within the context of concentrated solar power (CSP) performance. The Certified Energy Manager (CEM) must understand how to interpret and act upon performance data, efficiency, capacity factor, in relation to environmental impacts, all while adhering to specific U.S. regulatory frameworks governing energy projects and environmental protection. The core challenge lies in making informed decisions that optimize CSP plant operations to meet energy demands and financial goals without compromising environmental standards or violating regulations. The correct approach involves a comprehensive review of CSP performance data, including efficiency and capacity factor, and correlating this with reported environmental impacts. This approach is correct because it directly addresses the CEM's responsibility to ensure energy projects operate efficiently and sustainably, as mandated by U.S. environmental regulations such as the Clean Air Act and the National Environmental Policy Act, NEPA, which require monitoring and mitigation of environmental impacts. Furthermore, industry best practices and the CEM certification itself emphasize a holistic view of energy systems, integrating performance metrics with environmental considerations. This aligns with the ethical obligation of a CEM to promote responsible energy management. An incorrect approach that focuses solely on maximizing capacity factor without considering efficiency or environmental impacts fails to meet regulatory requirements. For instance, operating a CSP plant at a high capacity factor through methods that might increase emissions or water usage beyond permitted levels would violate environmental permits and regulations. Another incorrect approach that prioritizes efficiency metrics above all else, potentially leading to reduced output or neglecting necessary environmental controls, also presents regulatory and ethical failures. This could result in non-compliance with environmental impact assessments or permit conditions. A third incorrect approach that solely addresses reported environmental impacts without a thorough understanding of the underlying CSP performance data, efficiency and capacity factor, would be reactive rather than proactive, potentially missing opportunities for optimization and leading to inefficient resource allocation or continued noncompliance. Professionals should employ a decision-making framework that begins with understanding the specific regulatory landscape applicable to the CSP project, e.g., EPA regulations, state-level environmental laws. This should be followed by a thorough analysis of performance data, identifying any deviations from expected efficiency and capacity factor. Subsequently, these performance metrics should be directly linked to potential environmental consequences, referencing any environmental impact statements or permits. The final decision should be a data-driven, integrated strategy that optimizes performance while ensuring strict adherence to all relevant environmental regulations and ethical standards for energy management. Question 13. During the evaluation of a proposed wind farm development project, which approach best optimizes the permitting, environmental impact assessment, and community engagement processes to ensure regulatory compliance and project viability? Option A. Integrate the environmental impact assessment process with proactive, transparent, and continuous community engagement from the project's inception, ensuring all feedback informs the permitting strategy. Option B. Conduct a minimal environmental impact assessment, focusing only on legally mandated disclosures, and engage the community only after key project decisions have been finalized. Option C. Prioritize securing all necessary permits first, Then conduct a comprehensive environmental impact assessment and initiate community engagement only when required by permit conditions. Option D. Focus solely on the technical feasibility and economic benefits of the wind farm, addressing environmental and community concerns only if they become significant obstacles to permitting. The correct answer is B. Conduct a minimal environmental impact assessment, focusing only on legally mandated disclosures, and engage the community only after key project decisions have been finalized. Explanation: this scenario is professionally challenging because wind farm development involves navigating a complex web of regulatory requirements, environmental considerations, and stakeholder interests. Balancing the need for renewable energy generation with potential impacts on local ecosystems and communities requires meticulous planning and adherence to established processes. The permitting process, environmental impact assessment (IA), and community engagement are not merely procedural steps, but are legally mandated and ethically imperative to ensure sustainable and responsible development. The correct approach involves a proactive and integrated strategy that prioritizes early and continuous engagement with all relevant regulatory bodies and community stakeholders. This includes conducting thorough baseline studies for the EIA, transparently communicating project details and potential impacts, and actively seeking and incorporating feedback from local residents and environmental groups. This approach is justified by the regulatory framework governing energy projects, which mandates comprehensive EIAs to identify and mitigate environmental risks, and by ethical considerations that demand respect for community rights and the environment. Effective community engagement fosters trust, reduces opposition, and can lead to more robust and socially acceptable project designs, ultimately streamlining the permitting process. An approach that delays or minimizes community engagement and treats the EIA as a mere compliance hurdle is professionally unacceptable. This failure stems from a misunderstanding of the regulatory intent, which is to ensure that projects are environmentally sound and socially responsible. Ignoring or downplaying community concerns can lead to significant project delays, legal challenges, and reputational damage, all of which increase project costs and risk. Furthermore, neglecting to conduct a comprehensive EIA can result in unforeseen environmental consequences, leading to regulatory penalties and long-term ecological harm. Professionals should adopt a decision-making framework that begins with a thorough understanding of all applicable regulations, including specific permitting requirements and EIA guidelines for the relevant jurisdiction. This should be followed by a stakeholder analysis to identify all affected parties and their potential interests. A robust engagement plan, integrated with the EIA process from its inception, is crucial. This plan should outline clear communication channels, feedback mechanisms, and strategies for addressing concerns. Regular review and adaptation of the development plan based on EIA findings and community feedback are essential for successful and responsible wind farm development. Question 14. The risk matrix shows a moderate likelihood of reduced operational efficiency and a high potential for environmental noncompliance stemming from the aging infrastructure of a regional hydropower facility. The facility comprises a concrete dam, steel penstocks, and Francis turbines connected to generators. As the Certified Energy Manager (CEM) responsible for this facility, which of the following approaches best aligns with regulatory requirements and professional ethical obligations for ensuring sustainable and compliant energy generation? Option A. Conduct a detailed assessment of the generator's current energy conversion efficiency and implement immediate upgrades to the most underperforming units, while deferring non-critical maintenance on the dam and penstocks to manage immediate budget constraints. Option B. Focus on optimizing the water flow through the penstocks to maximize immediate power generation, assuming that the existing dam structure and generator technology are within acceptable operational parameters for the current regulatory period. Option C. Prioritize the replacement of the oldest generators with newer, more energy-efficient models, as this is the most direct path to improving the facility's overall energy output and reducing its carbon footprint without extensive investigation into the dam or penstocks. Option D. Initiate a comprehensive review of the dam's structural integrity, the penstock's flow capacity and leakage, and the generator's operational performance, cross-referencing all findings with current environmental protection regulations regarding water flow, sediment discharge, and aquatic habitat, and explore opportunities for optimizing renewable energy output. The correct answer is A. Conduct a detailed assessment of the generator's current energy conversion efficiency and implement immediate upgrades to the most underperforming units, while deferring non-critical maintenance on the dam and penstocks to manage immediate budget constraints. Explanation: Scenario analysis. This scenario presents a professional challenge for a certified energy manager, CEM, by requiring them to assess the operational integrity of a hydropower system's critical components, the dam, penstocks, and generators, in the context of potential regulatory noncompliance and environmental impact. The challenge lies in balancing the need for efficient energy generation with the imperative to adhere to stringent environmental regulations and ensure the long-term safety and sustainability of the infrastructure. CEM must demonstrate a comprehensive understanding of how these components interact and how their condition directly influences compliance with relevant environmental protection laws and energy efficiency standards. Correct approach analysis. The correct approach involves a systematic, multifaceted assessment that prioritizes regulatory compliance and environmental stewardship. This entails conducting thorough inspections of the dam's structural integrity, evaluating the penstocks for potential leaks or blockages that could affect flow and efficiency, and verifying the operational status and efficiency of the generators. Crucially, this approach necessitates cross-referencing findings with the latest environmental regulations governing water discharge, sediment management, and aquatic life protection, as well as energy efficiency standards for generator performance. The CEM must also consider the potential for renewable energy integration or optimization, aligning with the broader goals of sustainable energy management. This holistic view ensures that operational decisions are informed by both technical performance and legal/environmental obligations, reflecting the ethical duty of a CEM to promote responsible energy practices. Incorrect approaches analysis. Focusing solely on generator efficiency without considering the upstream and downstream impacts of the dam and penstocks represents a significant regulatory and ethical failure. This narrow focus ignores potential environmental violations related to water flow alteration, habitat disruption, or sediment accumulation, which are often governed by specific environmental protection acts. Prioritizing only immediate cost savings by deferring maintenance on the dam or penstocks, even if generators are performing adequately, is also a failure. This approach neglects the long-term structural integrity risks and potential for catastrophic failure, which could lead to severe environmental damage and significant legal liabilities under infrastructure safety regulations. Furthermore, neglecting to investigate potential renewable energy integration opportunities, such as optimizing turbine operation for variable water flows or exploring auxiliary renewable sources, represents a failure to uphold the CEM's responsibility to promote the most sustainable and efficient energy solutions available, potentially contravening broader national energy policies aimed at increasing renewable energy adoption. Professional reasoning. Professionals in this field should adopt a risk-based, compliance-driven decision-making process. This involves 1. Identifying all relevant regulatory frameworks and standards applicable to hydropower operations, including environmental protection laws, dam safety regulations, and energy efficiency mandates. 2. Conducting a comprehensive risk assessment that evaluates the technical condition of all critical components, dam, penstocks, generators, and their potential impact on regulatory compliance and environmental sustainability. 3. Prioritizing actions based on the severity of identified risks, with a strong emphasis on addressing any potential noncompliance or environmental hazards first. 4. Integrating operational efficiency improvements with environmental protection measures, seeking solutions that offer synergistic benefits. 5. Documenting all assessments, decisions, and actions thoroughly to demonstrate due diligence and compliance. Question 15. Performance analysis shows that a wind turbine's individual blade sections achieve a high lift-to-drag ratio at a specific angle of attack. Considering the operational goals of maximizing energy yield and adhering to energy efficiency regulations, which of the following aerodynamic considerations is most critical for optimizing the wind turbine's overall power coefficient? Option A. Disregarding the impact of blade pitch angle, as it primarily affects structural loads rather than aerodynamic efficiency. Option B. Maximizing the lift-to-drag ratio of each individual blade section at all times. Option C. Optimizing the tip speed ratio and blade pitch angle to achieve the highest possible power coefficient across the turbine's operating wind speed range. Option D. Assuming the theoretical maximum power coefficient is achievable regardless of wind speed or control settings. Correct answer is C. Optimizing the tip speed ratio and blade pitch angle to achieve the highest possible power coefficient across the turbine's operating wind speed range. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a certified energy manager, CEM, to interpret complex aerodynamic principles in the context of practical wind turbine operation and regulatory compliance. The challenge lies in distinguishing between theoretical aerodynamic efficiency and the practical implications for energy yield and operational integrity, all while adhering to the specific regulatory framework governing energy management in the relevant jurisdiction. Misinterpreting these aerodynamic factors can lead to suboptimal performance, increased operational costs, and potential noncompliance with energy efficiency standards or renewable energy targets. Correct approach analysis. The correct approach involves understanding that while maximum lift-to-drag ratio is a fundamental principle of aerodynamic efficiency for a single airfoil, it does not directly translate to maximum power output for a wind turbine rotor. A wind turbine's power coefficient is influenced by the entire rotor's interaction with the wind, including tip speed ratio, blade pitch, and the overall torque generated. The CEM must recognize that the goal is to optimize the power coefficient CP across a range of operating conditions, not solely to maximize the lift-to-drag ratio of individual blade sections. This aligns with the CEM's ethical responsibility to ensure the efficient and effective operation of energy systems, as mandated by professional standards and potentially by regulatory bodies overseeing renewable energy installations. The CEM's role is to apply aerodynamic theory to achieve practical energy generation targets, which is a core competency expected under the CEM certification. Incorrect approaches analysis. Focusing solely on maximizing the lift-to-drag ratio of individual blade sections is an incorrect approach because it overlooks the integrated performance of the entire rotor. This leads to a misunderstanding of how wind turbine power is generated and optimized. It fails to consider the complex interplay of factors that determine the overall power coefficient, such as the tip speed ratio, which is critical for achieving optimal energy capture. This approach is ethically problematic as it deviates from the professional duty to ensure the most effective energy generation possible, potentially leading to underperformance and missed efficiency targets. Assuming that the highest possible power coefficient, CP, is achievable at all wind speeds is also an incorrect approach. The power coefficient is a function of the tip speed ratio and blade pitch angle, and it varies significantly with wind speed. A CEM must understand that there is an optimal tip speed ratio for maximum CP, and this optimum may shift with changing wind conditions and turbine control strategies. Aiming for a theoretical maximum CP without considering operational realities and control system limitations is unrealistic and can lead to misinformed operational decisions. This demonstrates a failure to apply a nuanced understanding of turbine aerodynamics and control, which is a core expectation for a CEM. Ignoring the impact of blade pitch angle on aerodynamic performance is another incorrect approach. Blade pitch is a primary control mechanism used to regulate rotor speed and power output, especially at higher wind speeds. It directly influences the angle of attack of the airfoils and, consequently, the lift and drag forces. A CEM must understand how pitch control affects the lift-to-drag characteristics and the overall power coefficient to ensure efficient operation across the turbine's operating range. Neglecting this fundamental aspect of turbine control leads to an incomplete aerodynamic analysis and can result in inefficient energy capture and potential structural stress. Professional reasoning. Professionals in this field should approach such scenarios by first grounding their analysis in the fundamental principles of wind turbine aerodynamics, specifically focusing on the power coefficient, CP, and its relationship to the tip speed ratio and blade pitch. They must then consider the practical operational context of the specific wind turbine, including its control system and the typical wind conditions at the site. This involves consulting relevant technical documentation and potentially performing site-specific analyses. The decision-making process should prioritize achieving the most efficient energy capture within the operational and regulatory constraints, rather than pursuing theoretical optima that are not practically achievable. This aligns with the ethical obligation to provide accurate and effective energy management solutions. Question 16. The efficiency study reveals that a large-scale geothermal energy project is technically feasible for a new industrial park. The proposed plant layout, however, is situated in close proximity to a sensitive wetland area and a residential community. The project developers are eager to commence construction to meet renewable energy targets, considering the regulatory framework for geothermal development in the United States. Which approach to plant layout and resource assessment best balances efficiency, environmental protection, and regulatory compliance? Option A. Focus on maximizing the number of extraction and injection wells within the most geologically favorable zones identified in a preliminary resource assessment to ensure rapid energy production, with environmental considerations addressed only if mandated by regulatory bodies during the permitting process. Option B. Conduct a comprehensive, site-specific resource assessment that includes detailed geological, hydrological, and seismic risk evaluations, and design the plant layout to incorporate buffer zones around sensitive areas, robust wastewater management, and continuous seismic monitoring, aligning with all applicable U.S. federal and state environmental regulations and permitting requirements. Option C. Prioritize a layout that minimizes surface footprint and initial construction costs, assuming the resource assessment indicates sufficient thermal energy for the projected demand, with environmental mitigation measures to be addressed during the operational phase. Option D. Design the plant layout to utilize existing infrastructure wherever possible, even if it encroaches on buffer zones, and rely on generic environmental impact statements rather than site-specific studies to expedite the permitting process. Correct answer is C. Prioritize a layout that minimizes surface footprint and initial construction costs, assuming the resource assessment indicates sufficient thermal energy for the projected demand, with environmental mitigation measures to be addressed during the operational phase. Explanation. This scenario is professionally challenging because it requires balancing the technical feasibility and economic viability of a geothermal system with stringent environmental regulations and resource sustainability. The Certified Energy Manager CEM must navigate complex permitting processes, potential public opposition, and the long-term implications of resource extraction. Careful judgment is required to ensure the proposed design is not only efficient, but also compliant and environmentally responsible. The correct approach involves a comprehensive resource assessment that accurately quantifies the available thermal energy, considering geological stability and potential impacts on local hydrology. This assessment must be integrated with a plant layout that minimizes surface footprint, addresses noise and visual pollution, and incorporates robust environmental mitigation measures, such as wastewater management and seismic monitoring, and strict adherence to relevant U.S. federal and state environmental regulations, e.g., EPA guidelines, state-specific geothermal permitting. This ensures long-term sustainability and regulatory compliance. An incorrect approach that prioritizes rapid development without a thorough resource assessment risks overestimating the resource, leading to an undersized or inefficient plant and potential environmental damage. This could result in regulatory noncompliance, fines, and project delays or cancellations. Another incorrect approach that focuses solely on minimizing initial capital costs by neglecting comprehensive environmental impact studies and mitigation measures is ethically and regulatorily unsound. This could lead to unforeseen environmental consequences, such as groundwater contamination or induced seismicity, resulting in significant legal liabilities and reputational damage. A further incorrect approach that overlooks the potential for induced seismicity and fails to implement appropriate monitoring and mitigation strategies is a direct violation of best practices and potentially specific regulatory requirements for geothermal development in seismically active regions. This demonstrates a failure to exercise due diligence and a disregard for public safety and environmental protection. Professionals should employ a decision-making framework that begins with a thorough understanding of the specific regulatory landscape governing geothermal development in the project's jurisdiction. This includes identifying all applicable federal, state, and local environmental laws and permitting requirements. The next step is to conduct a detailed site-specific resource assessment, utilizing appropriate geological and hydrological expertise. This data then informs the plant layout and design, ensuring that environmental considerations, including mitigation strategies for noise, visual impact, water use, and seismic activity, are integrated from the outset. Finally, a robust stakeholder engagement process should be undertaken to address community concerns and ensure transparency. Question 17. The efficiency study reveals that the proposed solar farm's energy yield predictions are significantly lower than anticipated, potentially jeopardizing its financial viability. The project team is debating the most appropriate method for measuring solar radiation to validate these predictions. One proposal suggests using a pyrheliometer to focus solely on direct beam radiation, arguing it's the most potent form of solar energy. Another suggests relying on a historical sunshine recorder to gauge the general availability of sunlight. A third option advocates for using a calibrated pyranometer to measure global horizontal irradiance, acknowledging both direct and diffuse components. Which of the following approaches is the most professionally sound and compliant with typical regulatory frameworks for energy yield assessment in the United States for a photovoltaic solar farm? Option A. Solely utilizing a pyrheliometer to measure direct beam solar radiation, as this represents the most intense and valuable component of solar energy for energy conversion. Option B. Using an uncalibrated pyranometer to measure global horizontal irradiance, assuming that minor inaccuracies will average out over the long term. Option C. Employing a calibrated pyranometer to measure global horizontal irradiance, as this accurately captures the total solar energy incident on the plane of the photovoltaic panels, encompassing both direct and diffuse radiation, which is essential for photovoltaic energy conversion. Option D. Relying on historical data from a sunshine recorder to estimate the duration of bright sunshine, which can then be used as a proxy for overall solar resource availability. The correct answer is C. Employing a calibrated pyranometer to measure global horizontal irradiance, as this accurately captures the total solar energy incident on the plane of the photovoltaic panels, encompassing both direct and diffuse radiation, which is essential for photovoltaic energy conversion. Explanation. The efficiency study reveals a critical need to accurately assess solar resource availability for a new renewable energy project. This scenario is professionally challenging because the choice of solar radiation measurement instrumentation directly impacts the reliability of energy yield predictions, project feasibility assessments, and ultimately, the financial viability of the installation. Misinterpreting or misapplying measurement techniques can lead to significant under- or overestimation of energy production, resulting in non-compliance with performance guarantees, regulatory penalties, and reputational damage. Professionals must exercise careful judgment to select the most appropriate instruments and methodologies that align with industry best practices and relevant standards. The correct approach involves selecting instrumentation that accurately captures the specific type of solar radiation relevant to the project's technology and location, adhering to established measurement protocols. For photovoltaic PV systems, which convert direct and diffuse solar radiation into electricity, using a pyranometer to measure global horizontal irradiance, GI, is standard practice. GHI represents the total solar radiation received on a horizontal surface, encompassing both direct and diffuse components. This measurement is crucial for predicting the energy output of fixed-tilt or single-axis tracking PV systems. Furthermore, ensuring the pyranometer is calibrated according to recognized standards, such as those outlined by the World Meteorological Organization, WMO, or relevant national metrology institutes, is essential for data integrity. Adherence to these standards ensures that the collected data is comparable, reliable, and defensible for regulatory reporting and project financing. An incorrect approach would be to solely rely on a pyrheliometer for a PV system assessment. A pyrheliometer measures only direct beam solar radiation, excluding diffuse radiation. While direct radiation is a significant component, neglecting diffuse radiation would lead to an underestimation of the total energy available to the PV panels, particularly in locations with frequent cloud cover or atmospheric scattering. This failure to capture the full solar resource would result in inaccurate energy yield predictions and potentially noncompliance with project performance requirements. Another incorrect approach would be to use a sunshine recorder, such as a Campbell-Stokes recorder, as the primary instrument for quantitative energy yield assessment. Sunshine recorders are designed to indicate the duration of bright sunshine, not the intensity of solar radiation. While they can provide qualitative information about sunshine hours, they do not provide the irradiance data in W/M2 necessary for calculating energy production. Relying on such a device would lead to a fundamental misunderstanding of the solar resource's energy potential and would be professionally unacceptable for detailed energy modeling. Finally, an incorrect approach would be to use a pyranometer, but fail to ensure its calibration is up-to-date and traceable to recognized standards. Uncalibrated or poorly calibrated instruments introduce systematic errors into the data, rendering the measurements unreliable. This lack of data quality control undermines the entire efficiency study and can lead to flawed decision-making, potentially violating professional engineering ethics and regulatory requirements for accurate reporting. Professionals should employ a decision-making framework that prioritizes understanding the specific energy conversion technology, e.g., PV, concentrated solar power, the project's geographical location and its typical atmospheric conditions, and the relevant industry standards and regulatory requirements for energy resource assessment. This involves consulting established guidelines from organizations like the International Energy Agency, (IEA), or National Renewable Energy Laboratories, and selecting instruments that are appropriate for the task and properly maintained and calibrated. Question 18. The monitoring system demonstrates a consistent, albeit minor, deviation in the vibration signature of a critical gearbox component on a wind turbine, exceeding the manufacturer's recommended threshold by 5% for the past 48 hours, with no other immediate alarms or performance degradation noted. As a certified energy manager, CEM, operating under U.S. regulatory frameworks, which of the following approaches best addresses this situation from a risk assessment perspective? Option A. Immediately initiate a full shutdown of the turbine to prevent potential catastrophic failure and await a full diagnostic inspection. Option B. Continue normal operation as the deviation is minor and within acceptable operational tolerances for short-term excursions, scheduling a gearbox inspection during the next planned maintenance cycle. Option C. Analyze the specific vibration frequency and amplitude patterns to identify the most probable cause of the deviation and recommend targeted diagnostic tests or immediate corrective actions based on that analysis. Option D. Focus on adjusting the turbine's control parameters to compensate for the increased vibration, aiming to maintain optimal power output while the anomaly is investigated. The correct answer is A. Immediately initiate a full shutdown of the turbine to prevent potential catastrophic failure and await a full diagnostic inspection. Explanation: scenario analysis. This scenario is professionally challenging because it requires a certified energy manager, CEM, to interpret complex operational data from a wind turbine and assess potential risks without immediate access to all historical maintenance logs or manufacturer specifications. The CEM must balance the need for continued energy generation with the imperative to ensure safety and regulatory compliance, making a nuanced risk assessment crucial. The potential for equipment failure, safety hazards, and non-compliance with environmental or operational regulations necessitates a thorough and justifiable approach. Correct approach analysis. The correct approach involves a systematic risk assessment that prioritizes immediate safety and regulatory compliance while gathering further information. This approach is right because it aligns with the core ethical responsibilities of a CEM to ensure the safe and efficient operation of energy systems. Specifically, it adheres to the principles of due diligence and responsible management, which are implicitly or explicitly required by professional standards and potentially by broader energy sector regulations, e.g., those governing grid interconnection, operational safety, and environmental impact. By identifying potential hazards, assessing their likelihood and impact, and then developing mitigation strategies, the CEM acts proactively to prevent incidents and ensure adherence to operational parameters that are likely dictated by grid operators or environmental permits. This methodical process is the bedrock of professional risk management in the energy sector. Incorrect approach is analysis. An approach that immediately recommends shutting down the turbine without further investigation is incorrect because it prioritizes a worst-case scenario without a data-driven justification. This could lead to unnecessary downtime, lost revenue, and potentially a breach of contractual obligations to supply power without a clear regulatory or safety imperative. It fails to demonstrate a balanced risk assessment and could be seen as overly cautious to the point of being inefficient. An approach that suggests continuing operation as normal while waiting for a scheduled maintenance check is incorrect because it disregards the immediate implications of the observed anomaly. Monitoring system's demonstration of unusual behavior suggests a deviation from normal operating parameters that could escalate into a more serious issue before the scheduled maintenance. This approach fails to uphold the CEM's duty of care to monitor and respond to operational deviations promptly, potentially violating safety regulations or operational guidelines that mandate immediate attention to such indicators. An approach that focuses solely on optimizing the turbine's performance based on the current readings, without considering the potential underlying causes of the anomaly, is incorrect. While optimization is a key function of a CEM, it must be secondary to ensuring the integrity and safety of the equipment. Ignoring an anomaly in favor of performance optimization could mask a developing fault, leading to catastrophic failure, safety risks, and regulatory noncompliance. This approach demonstrates a failure to prioritize risk management over immediate performance gains. Professional reasoning. Professionals in this situation should employ a structured risk assessment framework. This involves 1. Identifying the anomaly and its potential immediate consequences, safety, environmental, operational. 2. Assessing the likelihood and severity of these consequences based on available data and professional experience. 3. Determining the urgency of the situation. 4. Developing and implementing appropriate mitigation strategies, which may range from further data collection and analysis to immediate shutdown or operational adjustments. 5. Documenting the entire process and the rationale for decisions made. This systematic approach ensures that decisions are informed, defensible, and aligned with professional ethics and regulatory requirements. Question 19. Process analysis reveals that a new wind farm development is being considered for a site with moderate but variable wind speeds in proximity to a residential area. The energy manager must recommend either a horizontal axis wind turbine (HOT) or a vertical axis wind turbine (VOT) technology. Which approach best aligns with professional responsibilities and regulatory compliance for this scenario? Option A. Rely on marketing materials and manufacturer specifications to determine the most advanced and efficient turbine technology available. Option B. Prioritize a comprehensive risk assessment that evaluates site-specific wind resource characteristics, potential environmental impacts, e.g., noise, visual, wildlife, and local zoning and permitting regulations for both HOT and VOT options. Option C. Select the turbine technology with the lowest upfront purchase price, assuming it will offer the most cost-effective solution for the project. Option D. Choose the turbine technology that is most commonly installed in similar climates globally, regardless of specific site conditions or local regulations. The correct answer is B. Prioritize a comprehensive risk assessment that evaluates site-specific wind resource characteristics, potential environmental impacts, e.g., noise, visual, wildlife, and local zoning and permitting regulations for both HOT and VOT options. Explanation. Scenario analysis. This scenario presents a professional challenge for an energy manager tasked with selecting a wind turbine technology for a new renewable energy project. The challenge lies in balancing the technical merits of different turbine types against the specific site conditions and regulatory requirements. A critical judgment is required to ensure the chosen technology is not only efficient, but also compliant with all applicable standards, safe for operation, and economically viable within the project's lifecycle. Misjudging these factors can lead to suboptimal performance, increased operational risks, regulatory penalties, and financial losses. Correct approach analysis. The correct approach involves a comprehensive risk assessment that prioritizes site-specific suitability and adherence to relevant regulatory frameworks, such as those governing renewable energy installations and environmental impact. This means thoroughly evaluating the wind resource characteristics of the proposed site, e.g., average wind speed, turbulence intensity, wind shear, and matching them to the operational envelopes and performance curves of both HOT and VOT. Furthermore, it necessitates understanding and applying local zoning ordinances, building codes, environmental protection regulations, and any specific permitting requirements for wind energy projects. The risk assessment should identify potential hazards associated with each turbine type in the given environment, e.g., noise pollution, visual impact, bird strike potential, structural integrity under extreme weather, and propose mitigation strategies. This holistic evaluation ensures that the chosen technology aligns with the project's objectives while minimizing potential negative impacts and ensuring legal compliance. Incorrect approaches analysis. Selecting a turbine technology based solely on perceived lower initial capital cost without a thorough site-specific risk assessment is an ethically and professionally flawed approach. This overlooks potential long-term operational and maintenance expenses, performance degradation due to unsuitable site conditions, and the risk of non-compliance with environmental or noise regulations, which could lead to costly remediation or project shutdown. Choosing a turbine technology based on its widespread adoption in other regions, without verifying its suitability for the specific local wind regime and regulatory environment, is also an unacceptable approach. This ignores the critical principle of site-specific design and can result in inefficient energy generation, increased wear and tear, and potential contravention of local planning or environmental laws. Opting for a turbine technology based on anecdotal evidence or marketing claims without rigorous technical due diligence and a formal risk assessment is unprofessional. This bypasses the necessary engineering analysis and regulatory review, exposing the project to significant technical and compliance risks. It fails to uphold the energy manager's responsibility to make informed, evidence-based decisions that protect the project's integrity and stakeholders' interests. Professional reasoning. Energy managers should adopt a systematic, risk-based decision-making process. This begins with a detailed site characterization, followed by an evaluation of available technologies against the site's specific conditions and the project's objectives. A critical component of this process is the thorough review and integration of all applicable regulatory requirements, including environmental impact assessments, zoning laws, and safety standards. The risk assessment should quantify potential risks and identify mitigation measures. This structured approach ensures that the final technology selection is technically sound, economically viable, environmentally responsible, and fully compliant with all legal and ethical obligations. Question 20. The monitoring system demonstrates a consistent clearness index over the past quarter, but the observed capacity factor has declined by 15%, and the performance ratio has dropped by 10% compared to the previous quarter. As a certified energy manager, which of the following analytical approaches best addresses the potential risks to the solar energy project's performance and financial projections? Option A. Focus solely on the capacity factor decline, as it directly represents the energy output relative to installed capacity, and recommend adjustments to the operational schedule to compensate. Option B. Analyze the interrelationship between the clearness index, capacity factor, and performance ratio, cross-referencing with meteorological data and system design parameters to identify specific causes for the observed performance degradation. Option C. Immediately initiate a full system diagnostic and maintenance schedule, assuming a significant equipment failure has occurred, to mitigate potential financial losses. Option D. Conclude that the decline in capacity factor and performance ratio is likely due to normal seasonal variations in solar irradiance and recommend continued monitoring without further investigation. Correct answer is D. Conclude that the decline in capacity factor and performance ratio is likely due to normal seasonal variations in solar irradiance and recommend continued monitoring without further investigation. Explanation. This scenario presents a professional challenge because it requires a certified energy manager, CEM, to interpret complex solar performance data and identify potential issues that could impact the financial viability and operational efficiency of a renewable energy project. The CEM must move beyond simple data reporting to a critical risk assessment, ensuring compliance with industry best practices and potentially regulatory requirements for performance verification. The challenge lies in distinguishing between normal operational variations and indicators of underlying problems that necessitate intervention. The correct approach involves a thorough analysis of the clearness index, capacity factor, and performance ratio in conjunction with expected meteorological data and system design specifications. This holistic review allows for the identification of deviations that could signal equipment malfunction, installation errors, or inaccurate data logging. For a CEM, this analytical rigor is ethically mandated to provide accurate assessments to stakeholders and ensure the project meets its intended energy generation and financial goals. Regulatory frameworks often implicitly or explicitly require diligent performance monitoring and reporting, making this analytical depth a cornerstone of professional responsibility. An incorrect approach would be to solely focus on the absolute values of the clearness index, capacity factor, or performance ratio without considering their interrelationships or contextual factors. For instance, accepting a low capacity factor without investigating the clearness index or performance ratio might overlook a systemic issue. Similarly, ignoring a declining performance ratio despite a stable clearness index could lead to unaddressed degradation or faults. These approaches fail to meet the professional standard of due diligence expected of a CEM. Ethically, this oversight could lead to misinformed decisions, financial losses for the project owner, and a breach of trust. From a regulatory perspective, such a superficial analysis might not satisfy requirements for performance verification or impact assessment, potentially leading to noncompliance. Professionals should approach such situations by first establishing a baseline of expected performance using historical data, design specifications, and relevant meteorological data for the specific location. Then, they should analyze the monitored data for deviations from this baseline, investigating the root causes of any anomalies by examining the clearness index, capacity factor, and performance ratio in concert. This systematic, data-driven, and context-aware approach ensures that potential risks are identified and addressed proactively, upholding professional integrity and regulatory compliance.